Final speaker of the session, Florence Archet. Thank you very much, Florence. So Florence is R&D manager at Dracula Technologies in France. And very good. Looks great. Very technical background.
Thanks, Christoph, for your kind introduction. As you said, I'm going to talk today about inkjet printed, flexible, and free design organic photovoltaic modules for indoor application. Before to start my presentation, I would like to thank all the organizers to give us the opportunity to present our work today. So my presentation will be divided into two parts. First, I will talk about inkjet printing for printed electric. And in the second part, I will talk in more details about organic photovoltaics by inkjet printing. So inkjet printing is one of the printing and coating techniques. Despite the need of a low ink viscosity, it allows to print a very smooth layer and it offers very high flexibility in the design. Indeed, inkjet printing is a fully digital printing and coating technique. It consists in generating few picometer droplets at a high frequency to print a design. It's a contactless technique. We distinguish continuous inkjet printing from drop on demand. For continuous inkjet printing, the droplets are continuously produced. Not required droplets are deflected. This allows to print at very high speed, so it's used, for instance, for the industrial labeling. At the opposite, on drop on demand, only the required droplets are generated. So this allows high resolutions. High resolution. So it's used, for instance, in the graphic field and in the printed electronic field. At Dracula Technologies, we use the drop-on-demand inkjet printing with piezoelectric print heads. So several parameters are important for the printing. First, the ink should be ejected from the nozzles. So the jetability is impacted by the ink viscosity, the surface tension, as well as by particle size. Thus, solvent surfactants are important parameters. Then for printing, the waveform is primordial. So in the printed, piezoelectric elements deforms whenever a voltage is applied to it. This will changes the volume of the ink chamber, causing the ink to move within it. So this will allow the ink to fill the ink chamber, or at the opposite, to be ejected and to form a droplet. The value of the voltage applied, as well as its duration, defines the waveform. The waveform will determine the droplet size and their velocity. As you can see on the drop watching, the aim is to obtain a very well-defined droplets without satellites. Another important parameter is drop spacing. So as you can see on the picture, it's important to obtain a good quality and good resolution. And finally, the other important parameters are related to the substrate. When all of these parameters are well mastered, we can obtain good quality layers. But before to obtain such a layer, we can face some challenges. One of the major challenges in inkjet printing is nozzles clogging. This occurs because of the evaporation of the ink in the printed. One way to avoid it is to use a higher boiling point solvent. Another fundamental challenge is to achieve a homogeneous layer throughout the drying process. We can indeed observe some covering, some frame effects. One way to solve this problem is to use a co-solvent. However, if we use a solvent with very different surface tension or vapor pressure, we can observe some pinholes after drying in the layers. We could also see some spreading effects or some poor wettability, like here in this example with a P-dot layer, or at the opposite, too high wettability. And finally, we can observe what I call the artistic effect. It's a combination of different issues, and it's absolutely not what we are looking for, as the quality of the coating directly